Hello everyone, welcome to lecture 23 of the online course on modern display technologies, flat panel display. Today's lecture will be on vertical alignment mode. We'll discuss the dynamics and overdrive. Here's the lecture outline. We'll look into the color shift compensation in the in-plane switching mode. Then we'll discuss about the vertical alignment mode, the structure involved, the materials and the voltage dependence transmittance it shows. After that, we'll go into the discussion of the optical response time. We'll talk about the Erikson-Leslie dynamics and the overdrive undershoot drive methods. So you can see that this particular lecture has three parts. The first one is basically a short recap of the color shift compensation in IPS mode using the chevron two-domain electrodes. In the second one, we'll introduce the vertical alignment mode in depth. We'll go into discussing its homeotropic structures, why it gives the best contrast ratio of any liquid crystal mode, and the material requirement and its stimulated voltage dependent transmittance curve. And next we'll derive the LC director dynamics from this Erikson-Leslie equation and obtain the closed form rise and decay time expressions, and then we'll finish with the overdrive undershoot voltage method, which is used in commercial LCD TV drive electronics. So here, welcome back. We'll start with a short recap of the color shift in the IPS mode LCDs. So here we'll say that the liquid crystal directors rotate in the plane of the cell, and the effective retardation seen by an eye basically changes the azimuthal viewing angle, and that basically produces a color tint rather than a bright a simple brightness change, right? So the color shift that you see in the IPS mode is a key visual artifact, okay, of this kind of LCDs at oblique azimuthal angle. Now the yellowish tint that appears near phi equals 45 degree, and you will see a bluish tint that appears near phi equals minus 45 degree, and these are basically caused by the asymmetric phase retardation happening off axis, right? Now if you remember the discussion earlier, that the yellowish shift at plus 45 degree and the bluish shift at minus 45 degree arise from the fact that the phase retardation error has opposite sign on either side of the polarizer axis. So how to fix this problem? The chevron or two-domain electrode design basically splits every pixel into two subdomains whose liquid crystal directors point in mutually opposite in-plane directions. So when you average out the transmitted color over the two domains, okay, the yellow and the blue error largely compensate each other and giving a perceptually neutral grayscale over a wide viewing cone. So you are basically seeing that here the two domains basically cancel out on averaging, giving you a effective symmetric color compensation, okay. So what is the strategy here? It is called the domain splitting philosophy. Though it sacrifices the uniformity within a particular pixel, but it allows you to gain the angular symmetry, so it reappears later also in the multi-domain vertical alignment cases, okay. Now with that, we'll move on to a completely different liquid crystal mode, which is called vertical alignment. So here we'll introduce the second major liquid crystal mode, okay, which is popularly known as vertical alignment or VA, okay. So This is also called homeotropic alignment and is a widely used liquid crystal mode for transmissive and reflective or projection kind of displays. Now, the emphasis on the geometry is that unlike the twisted nematic or in plane switching, where the directors lie roughly in plane, when you consider the vertical alignment, here the cells anchor the liquid crystal directors perpendicular to the glass at 0 plane. Okay, so that is why the name homeotropic. Now, between cross polarizers, this basically gives excellent dark state, because normally incident light sees no birefringence, right? Now, the three major advantages that this vertical alignment cells give you commercially is that you get very good contrast ratio. Okay, in fact it gives the best contrast ratio of any liquid crystal mode. The second thing is that the contrast ratio's remarkable robustness to the wavelength, cell gap and temperature. So unlike twisted nematic, where it is comparatively fragile to this kind of variation. And the third benefit is the response time, which we will see later on, right? So how this vertical alignment cell works? So at V equals 0, the liquid crystal director basically aligns perpendicular to the substrates. So you call it homeotropic anchoring. So that gives you normally black between the cross polarizers. And then, as we discussed, this gives the highest contrast ratio among all developed liquid crystal modes, and it is also very insensitive. This high contrast ratio is very insensitive to the incident wavelength, liquid crystal layer thickness and the operating temperature. Okay, so the vertical alignment cells also can switch faster than the corresponding homogeneous in plane switching type or the twisted nematic type cell. So the response time benefit is also there, as we have just discussed. So what are the applications? So in real world context, this vertical alignment is used both in liquid crystal on silicon, that is LCOS, okay, micro displays for projectors, where the single domain version excels because the viewing angle here is not a concern. And in direct view TVs and monitors, where multi-view or multi-domain versions will be needed to fix the narrow viewing angle, so there also this also becomes very important. So we will discuss this in the next lecture. So now let us focus more on the response time of an liquid crystal, of this liquid crystal layer, which scales as tau. Proportional, tau is the response time proportional to gamma 1 d square divided by k pi square. So here you can see these are all generic constants, you already know that. It's k is the elastic constant that governs the relevant deformation, right? So there are a couple of things here for the homogeneous, twisted and homeotropic cells, which are basically governed by splay, which is K11, twist the K22, and homeotropic is by bend, that is basically K33. Okay, so K will be K33 in this particular case. Now what are the important parameters? You can see that the time is basically proportional to the rotational viscosity times the cell gap squared, okay, and then it is divided by the governing elastic constant times the pi squared. Okay, so if you have a larger constant, that will basically give you a smaller response time. Okay, so we already understood this particular which k factor will be applicable in which case. Now the key physical fact is that the homogeneous, that is the splay, twisted and the homeotropic or the vertical alignment or band cells are each restored to equilibrium by a different Frank elastic constant, which are basically K11, K22 and K33, right? And for essentially all nematic liquid crystal mixtures, the ordering is typically that K33 is larger than K11 and then larger than K22. So this is the case for most of the liquid crystal mixtures, right? So here you can see that when K33 is larger, the homeotropic or the band cell has the largest K so it will definitely give you the fastest and the best response. So among the three types, the bend dominated homeotropic, that is the vertical alignment cell, will have the largest restoring constant, and hence it will have the fastest response time, and together they will make very good dark state and also give you the best contrast ratio. Okay, so here tau naught then can be written as gamma 1 d square divided by k33 upon k33 into pi square. Okay, so tau naught is basically the reorientation time, okay, or you can say the response time. Okay, and this tau naught, as I mentioned, is the LC director reorientation time. So it is basically the intrinsic response time scale that is set by the viscosity, the cell gap, and the elastic constant. Okay, now to achieve a full pi phase retardation, that means 100% transmittance in a transmissive cell, what you require, the required cell retardation d delta n, that differs by the LC mode, right? So for homogeneous cells and for homeotropic cells, that is the vertical alignment cells, the required d delta n is simply lambda over 2, okay, that you can see here. That has to be simply lambda over 2, that is basically the half the wavelength of the light, and this is the classic half wave plate criteria, right? So for a 90-degree twisted nematic cell, therefore twisted nematic cells, you can see that value is around 0.866 lambda, okay, and in other cases it's just 0.5 lambda. Okay, so here for the twisted structure, it basically guides light differently through the Gooch, Terry or the Maguin regime, and they basically require a larger retardation margin. That's why this relationship for 90-degree twisted nematic is different. Okay, so the first one, as I mentioned, it's for the homogeneous or homeotropic vertical alignment cells. The second one belongs to the 90-degree twisted nematic cells. So it's clear that you require a larger d delta n budget here, and that is one, this thing is one particular reason that tells you that the vertical alignment cells or the homeotropic cells or homogeneous cells are much simpler to optimize. Okay, now this slide particularly shows the voltage dependence transmittance of a vertical alignment cell. Okay, so here the simulated voltage transmittance or VT that you see of a single domain vertical alignment cell and the liquid crystal material that has been used to generate it, right? So this is the simulated single domain cell using the Mark's high resistivity mixture, that is MLC 6608, where we have considered d delta n to be 350 nanometer. Okay, so this MLC 6608 is a highly resistive negative dielectric anisotropic mixture that is needed for via operation, and here you can see the extraordinary and the ordinary refractive index. Okay, and the clearing temperature and the rotational viscosity, all parameters are mentioned. So physically you can see that at 0 volt, okay, the liquid crystal directors are basically vertical, so the cross polarizer is blocked, so the light is basically blocked between the cross polarizers, so that basically gives you zero transmittance or an excellent dark state, okay, at the low voltages. But as you see, the voltage is increasing, okay, slowly. So there is a threshold of say 2.1 volt, that is the RMS voltage. So this is the Friedrichs threshold. So here the liquid crystal directors reorient and the transmittance begin to rise. Okay, so this happens when the electric torque basically overcomes the elastic restoring torque and the directors begin to tilt away from the vertical, and that starts allowing the light to pass through. And then what you see that around 6 volts, okay, here Okay, RMS, you can see the green channel, this one, the green channel transmittance basically saturates to almost 100 degree, but note that the blue, this is the blue and this is the red. The blue one saturates slightly at different voltages, so blue one saturates at around 4 and red saturates even at higher voltages, and this is the origin of the color shift with gray level issue that the multi-domain and the field compensation schemes must also manage, that different colors basically saturate at different voltages. Now here we will discuss about optimizing this d delta n. So we will talk about the ideal and the practical target. So in principle 100% transmittance of a transmissive vertical alignment cell will only require that d delta n should be roughly equal to lambda by 2. So if you consider lambda to be 550, the human eye is basically most sensitive to the green light, that is lambda equals 550 nanometer. So in that case the minimum delta d delta n will be half of that, that is 275 nanometer, right? So this you can consider the theoretical minimum d delta n of about 275 nanometer, that is tuned to the eye's peak green sensitivity at 550 nanometer, and is only sufficient if you are willing to drive the cell to very high impractical voltage, right? Now the problem is that with this kind of minimum, the 100% transmittance will occur at very high voltage, and this is unrealistically high voltage. So what we have seen that the TFT backplane basically supplies a finite voltage swing, typically below 6 volt RMS. So your practical target should be to work within that limit. So in that case you should basically increase your DWN, d delta n. So if you go up to say 0.6 lambda, that comes out to be 330 nanometer, and that matches typically with the previous example that we have discussed of MLC 6608, where d delta n was around 350 nanometer, right? Here we will see the full directed dynamics equation for liquid crystal restoration under an applied field, which is also known as the Ericsson-Leslie equation. So this basically describes the directed dynamics, which will use that response time as well. So one thing to point out in this equation is that this is a nonlinear second order partial differential equation for the tilt angle, that is phi, okay, as a function of the position z through the cell and time t. So on the left hand side of the equation, this basically combines the elastic restoring term, that is the angle dependent effective elastic constant with the bending blending of K11 and K33, okay, and then you have a nonlinear gradient squared termed, okay, and then you have the final term, third term, that is basically the electric field driving term, right? So on the right hand side you have a viscous damping response, which is proportional to the rotational viscosity, that is gamma 1. So this is the equation. So here we are ignoring the backflow and the inertial effects, and we are considering that the liquid crystal director orientation angle, that is this phi, okay, this phi the same, okay, is function of z and t, and it basically obeys this Ericsson-Leslie equation we have just described, okay. So once again K11 and K33 are basically the splay and the band elastic constant, gamma 1 is the rotational viscosity, and this term epsilon naught delta epsilon E square is basically the electric field energy density, and phi is the tilt angle, liquid crystal detector tilt angle. So in general this nonlinear PDE can be solved numerically. So how do you do that? Let us see the small angle approximation here. So for small tilt angle, you can consider sin phi equals phi, and your k33 equivalent to k11. So that basically simplifies your previous equation, and this is the previous equation that can be now simplified to this particular form, which is pretty much linear and analytically tractable. So you just get k33 dou square phi dou z square plus epsilon naught delta epsilon e square phi equals gamma 1 dou phi dou t. So this linearized form is what that allows the closed form rise or delay time expressions that we will see in the next slides. Okay, so once you solve that closed form, you get a closed form solution by solving that linearized director equation between 10% to 90% transmittance through the cross polarizers, and that will give you that rise time. So tau rise can be given as tau naught by 2 v by vth whole square minus 1 whole inverse ln of this term. Okay, so here you have delta naught by 2 divided by sine inverse of square root 0.1 sine delta naught by 2 minus 1, and then you have the similar term here, but it is that 10% and this that 90%, right? So here you can see that V is basically the applied bias voltage, VTH is the threshold voltage, Friedrichs threshold voltage that you have seen earlier, and delta naught is basically the net phase change from V equals VB to V equals 0. So this is when the voltage is not applied, and this is when the bias voltage is applied. So one observation is that rise time is strongly voltage dependent, and it is slow near the threshold and very fast well above it. Okay, and similarly you can also obtain the decay time expression. Here it will be like the numerator will be 90%. From 90% you are coming down to 10% for the calculation of the decay time. So it is very similarly done. So you get tau decay will be tau naught by 2 ln sine inverse of square root of 0.9 sine delta naught by 2 divided by similar thing, just this will be now square root of 0.1. So what is this tau naught? This tau naught is the intrinsic liquid crystal reorientation time that you have seen earlier, which is given by gamma 1 d square divided by k33 pi square. So this is basically the natural time scale of both rise and decay, so it will be there, and then you have this additional factor coming in. So what you see here, that this decay time is something special. Unlike the rise time, the decay time, the field of relaxation is essentially voltage independent, because the voltage is now withdrawn. Okay, so now let us have a physical picture what sets this switching speed. So what we understood that tau naught is basically gamma 1 d square divided by k33 pi square. This is the single intrinsic time scale. Okay, and if you have a smaller cell gap d, or if you have larger constant k33, you can basically have faster switching. Now the rise time additionally depends on also how far above the threshold voltage the V is sitting. So if your V is very close to VTH, okay, then the rise is very slow. We have seen that graph, right? And if it is away from the VTH, that the rise is very fast. And the decay time depends only on tau naught and also on the bias induced phase swing, that is delta naught. So the decay time is independent of this drive voltage. Okay, so this asymmetry that you experience, that slow near the threshold voltage or threshold rise, okay, and then the decay is basically voltage independent. So these problems basically motivates a practical fix. So there we have to think of some kind of overdrive or undershoot method, which we'll be discussing next. Okay, so just one important thing to remember here is that there is an important asymmetry coming into this picture. The rise time is strongly voltage dependent, and it becomes very slow when the applied voltage sits just above the Friedrichs threshold, which happens often in practice for intermediate gray levels. And we have also seen, on the other hand, the decay time in contrast does not depend on the drive voltage at all once the field is removed. So this kind of asymmetry is the motivation for the overdrive and the undershoot voltage method that we will be discussing. The main purpose is to here come up with a clever waveform trick, not a change in the cell physics that could speed up the perceived response time. So with that, let us discuss this particular issue. So we understood the problem is for the gray levels near the threshold voltage where the rise time is very slow. Okay. So here we will look into the overdrive and the undershoot method. So this is basically a signal processing style fix for the slow near threshold response which are identified earlier. So let us consider a normally black vertical alignment cell which is biased just below the threshold. So for an intermediate gray level only slightly above the threshold voltage, tau rise basically tells us that the rise time would be very slow if we simply applied the target voltage directly. Okay, so what we can do? We can use the overdrive trick. So instead of jumping straight to the target voltage, apply a brief higher overdrive voltage, okay, and much higher overdrive voltage pulse, okay, to rapidly kick the director into motion, and then you drop it and hold the voltage at the actual target level that is required for the desired gray level. Okay, once it is reached. Okay, so the similar mirror image trick can be used for the falling edge, and that will be called the undershoot. So briefly drop the voltage below or to 0, and then apply a small holding voltage to settle at a new lower target gray level quickly. So let us understand this from this particular figure itself. So this is the overdrive and the underdrive voltage method for speeding up the liquid crystal rise and the decay times. That the top one shows the optical response, and the bottom trace is the corresponding voltage waveform. Okay, so this is the transmittance versus time, this is voltage versus time. So the dashed one is the normal rise and the fall, okay, but the solid one is basically the ones with this overdrive and undershoot voltages. Okay, so quickly you give this high voltage to do it, and then slowly you bring it down to the actual voltage level, so it settles down there. Okay, similarly here also you suddenly make it 0 and then you put it back to the level there, so it just comes down and then stays over there. So what you are doing, you are able to make the response much faster by tricking this thing, so which is called the overdrive and the undershoot voltages. So together the overdrive and the undershoot can reduce the liquid crystal response time by a factor of 2 to 3 times. So why this overdrive or undershoot works and why it is used? So physically the method exploits the fact that the response time is basically voltage dependent. So a large V by VTH ratio always switches faster. So the overdrive pulse briefly forces a large V by VTH, driving the LC director towards the target orientation faster than the direct jump would have done. And once that transmittance level reaches the desired gray level, you drop the voltage back to the correct holding value. So the liquid crystal settles without overshoot. And this is a lookup table driven technique that is implemented in the display's timing controller. So this is basically a hardware or the firmware trick, and there is no change in the cell physics required. So overdrive, undershoot, these are essential for LCD TV applications, particularly at cold ambient temperatures where gamma 1 and because of that your tau naught increases sharply. So to summarize, we have understood that the vertical alignment or the homeotropic modes, they provide the highest contrast ratio of any liquid crystal mode. So this contrast ratio is also robust to wavelength, thickness or temperature variation, and they provide very fast response time. The speed traces to the band elastic constant K33, which is basically the largest of the three elastic constants. Okay, because of that you get a very fast response time. Okay. The practical cell design also requires d delta n to be slightly higher than lambda by 2. You should go for 0.6 lambda to achieve the full transmittance within the realistic TFT voltage swing. We have also seen the Ericsson-Leslie equation, which is linearized for small voltages that can yield closed form rise decay times. And then finally the overdrive and undershoot method that could exploit the VY/VTH, that ratio dependence of the rise time to cut down the response time 2 to 3 times. Okay, so this is basically a driving scheme fix that you are giving, not a material fix. So what are the important things that remains? That single domain vertical alignment has one major weakness, that is a relatively narrow viewing angle for direct view application. So how you can fix it? You can use multi-domain vertical alignment approach, that is MVA, multi-domain vertical alignment, that allows splitting each pixel into typically 4 domains. So you can generalize today's chevron IPS idea and make it, and we will also study the compensation film schemes that could restore the wide angle contrast using the Poincare sphere design. And finally we turn to different fast switching modes, and that will be the optically compensated band OCB pi cells. So we will discuss this in the next lecture. Okay, thank you. If you have got any query regarding this lecture, you can drop an email to this email address mentioning the course name and the lecture number on the subject line. Thank you.